Welcome to our extended video on analyzing clustering approaches for the evaluation of emerging technologies within the domain of precision agriculture. We hope you enjoy our presentation. The transition towards a more sustainable economy requires innovations such as precision agriculture technologies. Theoretically, emerging technologies are characterized through various attributes such as radical novelty, uncertainty, prominent impact, fast growth, and coherence over time. Emerging technologies might also disrupt industries. For instance, established agricultural machinery manufacturers are confronted by emerging robotic or sensor technologies demanding for systemic changes in their current business models. Thus, the identification and evaluation of these technologies is important for companies to evaluate business opportunities, as well as for researchers and policymakers to support the transition towards a more sustainable economy. Our overall goal is to evaluate emerging technologies in the field of precision agriculture. Here, we concentrated on the two aspects, fast growth and coherence. To evaluate these aspects, we applied two different unsupervised machine learning algorithms and identified clusters consisting of papers based on semantic similarities.
We collected data from the Web of Science with the help of a suitable search string. Here, we excluded livestock, since we assume that the technologies identified for crop production differ significantly from those dealing with livestock. Based on title and abstract of the collected publications, we measure semantic similarities between the publications. These similarities are calculated with the help of the Padvisor software. The calculated similarities serve as input for the applied unsupervised machine learning algorithms. Namely, we compared hierarchical clustering and spectral clustering. For the hierarchical approach, we use a distance matrix and in a first step identify potential outliers. Second, we apply the Ward algorithm in order to extract homogeneous clusters. The spectral approach consists of two steps. First, by calculating eigenvalues and eigenvectors of the so-called Laplacian matrix, which is easily derived from the pairwise similarities, one calculates a vector representation of each publication. In the second step, the embedded publications are clustered by means of the k-means clustering algorithm. In both clustering approaches, the number of clusters is identified over a certain heuristic, since so far there is no method defining the optimal number of clusters. For the hierarchical approach, we use the silhouette coefficient, and for the spectral approach, we use the eigengap heuristic. Having identified the clusters, we use and combine cluster labeling by TF-IDF and mutual information-based labeling to describe the technologies. Finally, we check the results of the labeling approaches manually by reviewing titles and abstracts of the published publications. Having identified and characterized the clusters, our results have to be evaluated.
Let us first take a deeper look into the underlying data dealing with precision agriculture extracted from the Web of Science database. Overall, we collected information on 5,771 publications. The scientific output in the field of precision agriculture is constantly growing. In the last 10 years, more than 200 articles have been published each year. The results of the hierarchical clustering are visualized as cluster evolution over time. We identified 14 clusters containing 59 up to 2,190 publications in the diverse cluster. In the right column, you will find the final cluster labels. The evaluation of the development over time shows one large cluster with more than 2,000 articles. Here, the labeling approaches reveal that this cluster contains rather diverse topics. The general term frequency leads to the assumption that the cluster is about technologies for agricultural or biomass production, as well as technologies relating to Internet of Things. However, IoT or Internet of Things also occurs within the top 10 bgrams regarding the TF-IDF values, which is not the case for the highest ranked bgrams of the mutual information-based labeling approach. As these topics are rather diverse and the number of allocated articles high, a further subcluster analysis might lead to additional insight. In total, we identified 3 diverse clusters which do not contain a single topic. Beside the large diverse cluster, there are 4 rather old clusters, starting in 1993 to 1995. These clusters contain publications dealing with soil organic matter or soil organic carbon, which is cluster 1, or the cluster about chlorophyll, which is cluster 2, apparent electrical conductivity, cluster 3, and plant classification, which is cluster 5. Here, for example, cluster 1 is growing constantly but seems to grow relatively fast in the last years. The plant classification cluster includes articles about plant classification, phenotyping, and plant monitoring, and is similar to cluster 8, vegetation indices, whereas in here satellite images are frequently used for plant monitoring. Starting between 1996 and 1999, we identified 6 clusters. Articles allocated to cluster 6 mainly introduce technologies for conservation agriculture that represents a farming system that promotes minimum soil disturbance, maintenance of permanent soil cover, and diversification of plant species. The conservation agriculture cluster can be seen as constantly growing since 2007. Additionally, we found 3 rather young clusters dealing with unmanned aerial vehicles, autonomous machineries, and wireless sensor networks. To sum up, hierarchical clustering leads to rather inhomogeneous clusters. This can be seen by simply comparing the number of articles allocated to the clusters. Nevertheless, it is possible to identify similarities and differences in between the clusters and to identify different emerging technologies in precision agriculture. Furthermore, it is possible to analyze individual growth of the emerging technologies, as almost all clusters reflect an increasing research interest over time. However, as shown by the different labeling approaches and by manually evaluating the articles within the clusters, some clusters are not coherent, or coherence can be hardly derived. Let's now move on to the results of the spectral approach.
Here we identified 17 clusters. Cluster 15 can be considered as an outlier, since the publications herein deal with livestock, which we intended to exclude from our data. The other 16 clusters range from sizes between 150 publications for the youngest cluster, Cluster 2, IoT, starting in 2012, and 984 for one of the older clusters, number 16, dealing with disease detection. In contrast to the hierarchical approach, we identified only one diverse cluster containing 556 publications dealing with several decision support systems. Again, an iterative clustering within the diverse cluster might improve the clustering results. Besides cluster 5, we identified 6 older clusters starting between 1993 and 1995. 6 more clusters started between 1996 and 1998. Here, cluster 16 represents the largest cluster in our dataset, containing 984 articles, and thereby including almost twice as many articles as the second and third largest clusters. However, the cluster contains less than half of the number of articles than the biggest cluster derived from the hierarchical approach. The different cluster labeling methods reveal that articles in cluster 16 contain pest and disease detection technologies based on different imaging approaches. The second largest cluster within this group is cluster 14, dealing with technologies for measuring chlorophyll content or using this data for different purposes in terms of vegetation indices. Cluster 2, 7, and 13 are the youngest clusters in the dataset, with the first publication in 2006 for cluster 7. The labeling approaches reveal that Cluster 2 is about IoT technologies. Exemplarily, a closer look into the articles in Cluster 2 show publications dealing with technologies such as IoT-based systems for forecast crop forest, a smart water-saving irrigation system based on big data, or a cloud computing-based smart farming system for early detection of borer insects and tomatoes. Cluster 7 contains 272 publications and is about wireless sensor networks, and Cluster 13 deals with UAVs and drones. For example, the UAV cluster can be regarded as rapidly growing, while the cluster for disease detection is constantly growing.
Compared to hierarchical clustering, some similar clusters can be observed. However, only some of them allocate a similar number of articles, for example, wireless sensor networks and variable treatment or rate sprayer. Others, for example, soil organic matter or soil organic carbon or apparent electrical conductivity, contain a different number of articles. What is more, hierarchical clustering seems to lead to one cluster about plant classification, whereas spectral clustering results in different clusters, such as machine vision, harvest monitoring, and spatial variability. In hierarchical clustering, no specific cluster for IoT occurs, as well as articles related to UAVs are different to the spectral clustering method allocated to different clusters. To sum up, in our case, spectral clustering seems to outperform hierarchical clustering. However, both methods support the identification and analysis of emerging technologies. As spectral clustering seems to result in more specific clusters, it might also lead to a more precise analysis of growth over time. Lastly, regarding the different labeling approaches, we experienced the best results by considering a combination of both TF-IDF as well as mutual information-based labeling, in a combination with a closer look into the articles themselves.
In this part, we would like to dive deeper into our data and into the validation of our labeling approaches. Accordingly, we zoomed into the research published by the University of Bonn. In total, we found 41 articles published between 2002 and 2019. For the hierarchical clustering, most publications were found in the clusters plant classification and SOM-SOC. For the spectral approach, the focus lies on the clusters SOM-SOC or spatial variability. As containing potentially emerging technologies, we identified 7 younger articles within the clusters dealing with UAV and vegetation indices. Here we found different technologies, for example, WeedMap, which is about a weed segmentation and mapping framework processing multispectral images obtained from an UAV. The manual check of the publication's title and abstract show that the combined labeling approaches result in suitable labels.
Let us close with a brief summary. Our data reveals that spectral clustering seems to outperform hierarchical clustering for the analysis of scientific research publications in the field of precision agriculture. Also, it seems to be useful to use more than one labeling approach for the cluster characterization. We extended existing approaches for assessing emerging technologies by analyzing timely development of clusters to assess fast growth and coherence, two main characteristics of an emerging technology. Finally, we dived deeper into the clusters and identified potentially emerging technologies developed at the University of Bonn. Still, some limitations need to be considered, as we identified additional potential outliers based on both approaches. These outliers should be excluded to further evaluate coherence and growth. In future work, the bridging of patent data and scientific data is one of our biggest challenges, as well as the operationalization of the remaining attributes of emerging technologies.
Thank you for your attention. We are looking forward to discuss our results during the Q&A session.